Welcome to the Merlin and Metro News Network. Our program today continues our in-depth look at the DC distribution system. During our previous program, we talked about the general theory behind the individual systems that make up the distribution system. Now we're going to begin discussing how this theory is actually applied and some of the technical details of this system. Again, remember that we are only discussing direct current or DC power only. So get comfortable, sit back, and let's continue with our discussion of the DC distribution system.
The battery control system is shown in this simplified diagram. Principal components are the batteries themselves, the battery fault control box, the battery switches in the cockpit, and the associated relays to connect all these components together. 3 major current-carrying relays are included in the circuit. Each battery's respective relay, which connects or disconnects the aircraft to the aircraft circuitry, and the battery bus relay, which connects the current from both batteries and the auxiliary power unit to the buses. The battery control system has several key functions, which we'll divide into 2 categories: those accomplished by the pilot manually and those which occur automatically. The pilot functions include being able to connect the batteries to the aircraft system and to the battery bus, to be able to selectively disconnect each battery, and to be able to put the batteries back on the line through a reset function, should the battery fault system disconnect them automatically. The automatic functions include the disconnection of both batteries, should there be an actual fault with the battery wiring, and to continue to disconnect a malfunctioning battery system, even if the pilot attempts to reset it. Indication functions of the battery control system are to provide the pilot with indications of whether each battery is connected to the system by means of a battery disconnect light, to provide an indication of the battery temperature through a temperature indicating system, and to indicate when the battery fault system has removed the batteries from the aircraft's bus through means of a battery fault light. A voltmeter is also provided that allows determination of the voltage present on the aircraft's bus and the voltage of each battery. The battery control system sequence is as follows. The pilot moves the battery switches to the on position. Then the battery relay closes, connecting the battery to the aircraft's electrical system. Then the battery bus relay closes, connecting batteries to the bus system. At this point in time, the battery fault system is not active, so the relay within the fault control box is relaxed. This is due to the fact that both generator systems have not been activated, a prerequisite to arm the fault detection circuit. After the fault system has been activated, an indication of a battery wiring malfunction will cause the fault system to trip and disconnect the batteries. If this occurs, the pilot would attempt to reset the batteries. The reset sequence is as follows. After the engines are operating and both generators are placed online, that is, providing power to the bus system, a condition needed to arm the fault protection circuit, 2 generator output sense relays will close. These relays are part of a circuit that provides power to a relay coil located inside of the battery fault box. Because no fault in the battery wiring has been sensed at this time, this power will have no effect. But should a fault occur, the power provided through the generator output sense relays is what enables the battery fault box to disconnect the batteries. Included in the same circuit is the battery fault reset relay. In its relaxed state, it provides a path for current to flow to the fault box and arm the system. If a fault is sensed and the system disconnects the batteries and battery bus relay, the functions are as follows. First, the pilot moves the battery switches to the reset position. The switches are spring-loaded and will not stay in reset without the pilot holding them in that position. Next, the battery fault reset relay will energize. The relay is connected into the circuit in such a way that when it is actuated, it will break the arming circuit, which then interrupts power to the battery fault box. This will cause the relay inside the fault box to relax. which will in turn again allow the batteries to be reconnected to the aircraft wiring. The pilot now moves the battery switches to on. If there is not a fault in the battery fault feeder lines, each battery relay will close. And then the battery bus relay closes. But if there is an actual fault with the battery wiring, the fault system will detect it and disconnect the batteries and battery bus relay again. The logic of the battery control system is as follows. If the battery switch is moved to the on position and the battery has electrical power available and the relay within the battery fault box is in the relaxed position, then electrical current should flow from the battery, through the battery relay, through the battery switch, through the closed contacts of the battery fault relay, and return to the battery through the aircraft structure. If this happens, the battery relay will close, and the battery will be connected to the aircraft's wiring system. The batteries are now connected to the aircraft wiring. Now their power must be supplied to the aircraft's bus. The logic of this is, if power is supplied by either battery to one side of the battery bus relay, and if either battery switch is in the on position, and the relay inside the battery fault box is in the relaxed position, then the battery bus relay will close and connect the batteries to the bus system. As you can see, the battery fault system controls both the connection of the battery to the aircraft wiring and the application of the battery's power to the bus system. The APU, an additional source of power, is also connected to the aircraft electrical system through use of the battery switches. There do not, however, have to be batteries installed for the APU to be placed online.
Before we get into the indicating systems that monitor and provide information on the DC distribution system, let's stop and briefly review what has been covered so far. By now, you should have a better understanding of what happens when you move the battery switches to on. You should be well aware that the battery fault and generator fault systems are different and totally independent. Now, the purpose of the fault transformers and how they work should be clear as well. If there are questions on any of these items, it is probably a good idea to stop the tape and review them further. Ready to go? Let's now continue on with the DC distribution, indication, and monitor systems.
The voltmeter system allows the pilot to determine the voltage being produced by each source of electrical power available to the aircraft and the voltage level present on the aircraft's bus. In order to accurately measure the voltage of each source, the source must be isolated from the aircraft electrical bus. In the case of the batteries, the battery voltage should be read with the respective battery switch in the off position. The same is true for the generators. The APU voltage must be read with the battery and generator switches in the off position in order for the reading to be accurate. The battery temperature circuit is installed to warn the pilot of an impending battery thermal runaway. Hot batteries do not always indicate thermal runaway, but a thermal runaway will always generate heat. A temperature indicator installed in the cockpit provides a reading in degrees Fahrenheit for each battery, and warning lights that are triggered by either battery. The yellow light will illuminate if either battery reaches 120 degrees. At 150 degrees, the red light will illuminate. There's also a range extend switch to allow temperature below 100 degrees to be read. A test switch is incorporated in the circuit to check the system for proper operation. The battery disconnect system is installed so that the pilot may accurately know whether each battery is connected to the aircraft wiring. In our previous program, we mentioned a device called a series parallel relay. Let's now discuss the function of this component and the effect it has on the electrical system. Remember that electrical loads can be connected in either series or parallel. Electrical sources can also be connected in series or parallel. When sources are connected in series, their total output voltage is the sum of both sources. A classic example is an ordinary flashlight. Each of these batteries has a voltage of 1.5 volts. But when we install them in the flashlight, they're in series and have a combined voltage of 3 volts. During engine start, a tremendous amount of electrical power is required. If the start is being made using only the aircraft's batteries, the amount of power available may be marginal under some temperature conditions. To provide more starting power under these conditions, a circuit is installed, which, when selected by the pilot, allows the batteries to be connected in series during the engine start cycle. The batteries are normally connected in parallel to provide a bus voltage of 24 to 28 volts, depending upon the condition of each battery. During engine start, the high demands placed on the batteries will cause this voltage to drop. By connecting the batteries in series, the starting bus voltage is substantially higher and will remain so during the starter motor operation portion of the start cycle. The series parallel system is only active during the engine start cycle. Control of this relay will be explained more fully in the program on the engine starting system. In order to provide a means to connect electrical power to the aircraft from a ground power source, an APU plug and associated wiring are provided.
All of the theory and details of a system are always just part of the story. Of equal importance is the insight, the things that you only learn from actually troubleshooting and maintaining the system. In our next section, we're going to include some information you usually won't find in this type of program. Some real-world details about the system.
Proper operation of the DC distribution system is an absolute necessity for successful operation of the electrical system on board the aircraft. Let's look at some important facets of the distribution system. An area frequently overlooked in troubleshooting efforts is the means for current to return to the source, the grounds. One of the most baffling problems a mechanic can be faced with is a loose or intermittent ground. Even if the ground feels tight, a visual inspection is still in order. Any signs of arcing or overheating are definite causes for further investigation. Connectors are another source of electrical problems. The battery connectors are easily overlooked in troubleshooting efforts. Again, any sign of overheating or arcing needs further investigation. The fault detection systems of both the battery and the generator circuits can be sources of aggravation. Much of this trouble can be attributed to by interference from other circuits on the aircraft, rather than actual faults. The fault detection system works on the basis of equilibrium, a state wherein the fault detection transformers provide a variety of polarity opposite signals to the fault detection box. The signals produced by the transformers, although relatively small, are strong enough to accomplish the task. The trick is to get these signals from the X1 and X2 connectors unmolested through approximately 200 feet of wire to the fault box. For maximum protection, the conductor carrying the signals is a special conductor called shielded wire. Shielded wire has two important properties that make it ideal for this installation. The shield around the insulated conductor provides physical protection to the signal conductor. The shield also provides protection around the sensitive conductor to protect the signal it carries from being affected by induction. We learned that all conductors, while carrying current, radiate a magnetic field. The field's strength depended upon the amount of current flowing. Because wires are routed in bundles, tightly grouped together, the small magnetic field of one wire may cause a small voltage to be induced into an adjacent wire by a property called transformer or inductive action. Suffice to say that these induced voltages are small and practically unmeasurable. Since most circuits in the aircraft function on 28 volts and consume a measurable amount of electrical power, they do not even notice these tiny induced voltages. On the other hand, conductors carrying millivolt signals, such as the fault signals, can be affected. These voltages induced by transformer action are better known as spikes. Shielded wire electrically protects the conductor within it by absorbing the radiated signals around it. It acts like an electrical sponge, drawing the potentially interfering magnetic fields around it and safely dissipates them to ground. This property of shielded wire is very effective, but can only function or protect in this installation when only one end of any given segment of the shielded conductor is grounded. Briefly, the theory behind this function is that harmful radiated fields are absorbed by the shield and harmlessly routed through the one grounded end and dissipated into the aircraft structure. The signal cannot re-enter the shield because it does not see another ground and there is no complete circuit. This figure shows an incorrectly installed shielded wire. The opposite end is also grounded. Again, the shield will absorb radiated magnetic fields that produce small currents, routed to one end of the ground and into the structure. Unfortunately, that signal will not dissipate into the structure, but has a path for it to enter the shield at the other end. This new signal flow itself produces a tanking effect around the conductor because of the low resistance of the shield. The middle conductor signal may now be affected by the surrounding blanket of radiated fields. It is important to note that the ground for the shield could be anywhere in the middle of the segment and produce the same ill effects. It is imperative this condition be prevented. It is equally imperative that such conditions be found and corrected using accepted electrical maintenance practices. In many cases, the shield inadvertently and intermittently touches the structure through its routing, making for a difficult situation to detect, much less repair. Suspected wire segments should be replaced using correct and safe routing. As in any troubleshooting of theory-related systems, use logic and common sense in attacking the problems. Look at the wiring diagram and isolate the fault signal portion of the circuit. If a copy machine is available, copy the relevant portion of the wiring diagram and use colored pencils or similar marking devices to highlight the segments in question. This will lift out only the circuit affected. Another suggestion is to redraw the segment in question on a scratch paper, omitting surrounding wiring. Now, using simple logic and common sense, isolate and check until the defective part is found. Then repair or replace as necessary. Sometimes theoretical circuitry and systems scare mechanics. The water analogy still holds and is equally simple. The mere fact that these errant signals are difficult to detect and measure does not change the theory. The theory holds and has since its first mention. Because the errant signals are small and difficult to detect, troubleshooting tools and equipment are very important. Quality test equipment produces quality results. Take a moment and study the use of meters. Although more sophisticated equipment is available, it requires more in-depth know-how to properly use, such as an oscilloscope, digital multimeter, and so on. Mastering simple multimeter techniques will suffice to troubleshoot these systems. Another source of errant spikes are coils, such as are found in valves, solenoids, relays, and motors. Here's a typical circuit involving a switch and a solenoid valve. The solenoid valve, of course, uses a coil of wire to produce a magnetism, which is used to move the valve. As current flows through the coil, a magnetic field radiates outward around the coil. When the switch is turned off, the magnetic field around the coil collapses. The collapsing field cuts across the coil wires, which induces a voltage in the coil. This is, in fact, how a generator produces electricity, as we will discuss in our next program. Although the amount of current produced by this action is very small, the voltage can be quite high, since the numerous turns of wire collectively produce significantly high voltage. Another noteworthy property of this induced voltage is that the polarity, or flow, is backwards from what it was originally fed. Hence it wants to go back to its source. When the switch opens, it cannot get back to the battery, so it tries to use other circuits to accomplish this. Motors, lights, and other significant users of electricity are unaffected, but small voltage circuits can be. Improperly shielded wires are a prime target for these reverse spike voltages to enter and disrupt a normally at-rest circuit, like the fault detection system. The most popular method to suppress these coil spikes is the use of a simple diode. This installation is an example. Current normally flows in this direction. Because the diode is polarity sensitive, it blocks this positive flow of current. Now opening the switch, the field collapsing induces a voltage. This illustration shows how the now reversed polarity backs up. Since it is backing up, this end is negative. It cannot jump through the open switch, but does want to flow into the adjoining circuitry. To prevent this, the diode, because of its polarity positioning, detects the reversed polarity spike and routes it harmlessly to ground. Remember, diode installations are used on high spike-producing components, such as large relays or valves. The obvious drawback is that the diode is another component that can fail. Diodes should only be used when all other methods are exhausted. The proper corrective measures for fault-tripping spikes is to ensure proper shielding of signal conductors. Another nuisance area are repaired or improperly installed connectors, such as crimped pins and connectors, crimped terminals, and of course, crimped splices. These devices are manufactured in numerous sizes, both in the size and gauge wire it will accept, as well as the size of connecting stud or terminal post. There will be cases when abnormally small wires are crimped to larger terminals. The same applies to crimped pins or splices. This exaggerated example shows what we mean. What can happen, as is shown here, is that the conductor's insulation is crimped. The worst part is that the crimping then hides the mistake and later makes it hard to detect. Simple oversights like this become nightmares due to their erratic, intermittent nature. Logic, common sense, and knowledge are your best defense for attacking these types of problems. The need for understanding the basic electrical principles cannot be overemphasized. If you're not absolutely clear on what has been covered, re-watch the last 2 tapes again, and by all means ask questions.
Well, that does it for the DC distribution and control subject. Hopefully, we've made everything clear up to this point, and you've gained a better understanding of how these critical systems work. Our next 2 programs will cover the DC generation system, which is the backbone of the electrical power supply for this aircraft. Until then, good flying and good maintenance.